How are you? Just finished that measurement. I talked to Scott the other day. You guys had some visitors.
Yes.
Did it go well?
Yes, yeah, it actually went much better. We visited a couple of weeks ago, and then we ran into a few issues with a cable and things like that, which we couldn't troubleshoot immediately.
Oh, yeah.
Everything was quick, I think.
Very good. That's always good.
And we have room for improvement too, so.
Very nice.
So, and we also learned a lot about the instruments.
You moving on to a new project?
So this is probably gonna go on for another few months, I think, because they are working with NASA and they're getting their Part B funding to move on with more testing.
Oh, very good.
What they tested is the engineering unit, and they want to do some modifications to it by adding like a stepper motor and things like that. So, and what we learned was that we have so much thermal mass, it takes so long for it to cool down inside the TVAC. And I think that's something they feel like they could change with the design itself. So they're gonna test another engineering unit probably in like a couple of months, and then the flight unit. So I think it's gonna go on for another.
What mission is it for?
Not exactly know what they're flying it on, but it's this concept of Doppler wave temperature sounding that they want to get into it more.
Very nice. Oh, man. How's it going? You'll have time to come by later? All right. Very good, very good. All right, guys, let's go ahead and get started. Okay, so yeah, cold day, I guess. So everybody's kind of arriving slowly, but that's okay. All right. So I just want to remind everybody, since there was some questions about, what can be done for their grades and things. The course is graded based on straight points, no curve. So here's the rubric that we've had since day one in the beginning of the course. Your final grade is going to be your weighted superposition or weighted summation of, or weighted average of your homework scores, your midterm score, final exam. The midterm was 25% and the final exam was 25%. So your score on that, you multiply that by the ratio to the total and you get your contribution of your midterm to your final grade and so forth, right? There are 7 homeworks for 50% for all of those. So what I'm announcing today is that if you did bad on midterm, then we're going to offer a extra some points over here, right? So you can't get better than 100 in the class if you did perfect on everything, but there will be an extra assignment that I'm going to give you. It's going to be a project. You're going to read a paper and recreate some simulation results and provide me a report that shows you put in enough effort to understand it and recreate the results of the paper. And that will give you a little boost so that you can correct any problems you had in your midterm. And you might want to take advantage of it anyway, because that'll help you on the final. So even if you're doing well, if you do the project, then at least it'll help you out if you don't do well on the final, right? So anyway, I'll announce that in the maybe next week, and I'll give you a list of possible papers to read through, and then you'll have to study the paper, analyze it, and recreate some of the simulation results or whatever results they have, derivations if you have to, and write it up in some kind of report. All right? Okay, good. All right. All right, so you'll know what grade you get based on this calculation. There won't be any curving or anything. Great. So yeah, so down here I say there will be no curve, but if you bomb an exam, please see me for a possible extra credit work. So that's what that is. It's going to be some kind of project. All right. Very good. All right. Any questions on that? Very well. Okay, so what are we talking about? We are trying to solve the inhomogeneous wave equation. We have derived the inhomogeneous wave equation based on vector potential theory, and we now can solve for radiated fields, E and H, due to current distributions that are arbitrary in shape, distributed throughout volume, for both electric and magnetic type, right? So we found, or we followed this path. We have sources. So what does it mean to solve an electromagnetics problem? It means to solve Maxwell equations, to take the coupled differential equations, which have E and H as vector field solutions to given sources on the right-hand side, J or M, right? So if we do the direct path or integration path here, the final solution is E and H, given J or M, right? We can go directly using the integration path one, and we saw last lecture that provides some difficulty because we have differential operators on the right-hand side of our inhomogeneous wave equation. So that is difficult to, we can't solve it using the Green's function approach, right? Maybe there's a way to do it, but it's more difficult. Another approach is to take the auxiliary path, path two. And in path two, instead of calculating E and H directly from J and M, we calculate these auxiliary potentials, magnetic vector potential A and electric vector potential F. By calculating these in terms of J and M as an intermediary quantity, we're able to then obtain E and H from the A and F through a differentiation operation. And we derived what these equations should be. We said that A is given by the spatial convolution of the Green's function, which is the solution to the differential equation, the inhomogeneous wave equation, for a delta function input. Because the source distribution is linear, we can break up that source distribution into a bunch of point sources, a bunch of delta functions. And we know what the solution or the radiation due to, or vector potential due to a point source is, right? So we can scale it. We can scale the radiation due to a point source. So e to the minus j beta r over r is the Green's function, or the radiation due to a point source. We scale it by the current density. So it gives it a vector nature and it gives it a magnitude and phase. We scale that point source with the starting magnitude and phase and direction of the current density at that given point. We calculate the vector potential at some observation point, and then we store it. And we go to the next point in the source, new r prime. We weight a point source by that new j, and we add it up at the observation point as well. It's a process of adding all this up is nothing but integration over the volume of the source, right? Superposition. Very good. So A, you can find in terms of J. Now, given a J, you can find this quantity A, right? Given an M, you can find this quantity F, where M is the magnetic current density. Once you have A and F, then you can go to this path, and by the process of differentiation, curl operation, gradient, divergence, this is all differentiation. Whereas here we did integration. So it's integration path. Here we're going as a differentiation path. We can find the electric field as the superposition of the contribution due to the electric current and the contribution due to the magnetic current, if both exist in general, right? And the formulas are explicitly stated here, derived these on last lecture. All right, so now you should feel very powerful. Now you can take a current density, any distribution, any shape on any surface, or just suspended in free space, and you can calculate the electric and magnetic field everywhere in space due to that. Which is a major operation, right? That's it. That's an accomplishment. Now, finding what this J and M is, that's the last part of it, right? You have the apparatus, the machinery, the framework to calculate E and H due to a J and M. So now, how do we get J and M, right? We'll do that next lecture, or no, next semester. There's numerical ways to calculate this exactly, and there's ways to estimate it based on some approximations we'll learn next lecture, which is like physical optics and so forth. All right. So now that we've figured out this entire machinery, we just need to start to estimate what J and M should be. All right. Good. All right. So now calculating these integrals, as we said before, calculating these integrals is difficult, right? Because r is changing for each r prime. Remember what r is. R is equal to, let's go back to this slide here, right? So the idea is we have a current density J. That current density can be broken up into a superposition or represented in terms of a collection of point sources, each at a different spatial location, R prime. Each of those point sources can be weighted by the current density at that point. So I have some point source, and I can weight that point source by the current density within that at that point. And then I can say the superposition, the collection of all these weighted point sources is a discrete representation of my continuous current density J, right? And in the limit, it's exact, right? Okay, so finding the solution to this wave equation for a delta function and put weighting alpha, where alpha is nothing but the current density at that point, and doing it for all of the delta functions or all the point sources in the collection. And by linearity, I can feed one of these through the differential equation at a time, get the magnetic vector potential at the observation point, and then I can feed the next one through and add it to the result, the cumulative sum. That process is nothing but spatial convolution. The problem here, though, is this R is changing. So let's see what R is. R changes with the integration variable, right? Okay, so it's going to do that as well in the far field approximation, which I'm alluding to, but it's an easier integral to calculate in general. Okay, good. So anyhow, let's specialize the case to the far fields. We looked at this before. We said in general, a far field has three components, r, theta, and phi, right? And these have various amplitude dependencies with respect to the radial variable. And we took that distribution. We said, okay, let's factor out an e to the minus j beta r over r. Whatever remains in each of these three components, we call a prime, a prime, a r prime, a theta prime, a phi prime, right? Okay. Now we take this expression and we plug it into our E in terms of potential A. All right. And we turn the crank. We did all of that, right? So I went through all of this for you. And in the end, the conclusion we found was that the electric field in the far field can be found by simply multiplying minus j omega into A prime, if you will. But A prime is nothing but e to the minus j beta r removed from A theta. So if you put that back into it, it's nothing but A theta without the prime. So that means in the far field, E is equal to minus j omega A, E due to A, right? But remember, this A is going to have in general R component, theta component, and phi component. So ignore the R component because we know it cancels out. We know it. If we were to carry out the other operator, which is the plus 1 over j omega mu epsilon, gradient to the divergence, then we would see it cancels out by what we did before, right? So ignore the R component, keep only the transverse components, and we can calculate E from minus j omega A, H from minus j omega F, and then, of course, we can find H from E whenever we have E or H, we can find the other field, right? Okay, great. Okay. So we have shown that in the far field, E and H are orthogonal and form TEM to R modes. What does that mean, TEM? Remember, what is TEM? Very good. That means the electric and the magnetic field are transverse to R, right? And R is the radial direction, which means that if we look in the radial direction, the electric field and the magnetic field are orthogonal to the direction of propagation. It's a plane wave with respect to R, right? Locally. So E is equal to minus j omega A, and then we can find H. Because of this local plane wave relationship, we can use the plane wave approximation. All right. So to find E given H, or to find E and H given a current distribution, we first need to find A due to J. We saw that. But for both near and far field calculations, so let's go to the geometry here, right? So for near field calculations, it's much more involved. this point R is in the near field, right? So we have this current density here, just some blob in space of current J. The position vector pointing to some point in that blob is R prime. The position vector pointing to the observation point where we want to calculate the field is R. And what matters is the spherical wave emanating from the point source, right? So it's going to be some spherical wave that's emanating from. So let me clean this up. Emanating from this current density, right? So we need capital R, which is equal to R minus R prime. All right, good. Now, how do we find what R is? R is the length of this vector here. How do we find what that length is? We use the law of cosines. There's a triangle here, which is not a right triangle. So when it's not a right triangle, you have to use law of sines or cosines. We're going to use the law of cosines, right? And the law of cosines is R squared is equal to, so that length up there is R, right? R squared is equal to, okay, so when there's no vector on top, that means the length of that vector, right? R squared is equal to R little r squared plus R prime squared plus 2 or minus 2R R prime cosine psi. I think it's like C squared equal to A squared plus B squared minus 2AB cosine theta is what I remember. But this is the same thing, all right? So you can find the length of that side using the law of cosines. All right, if observations, however, are made in the far field instead, right? The rays R, big R and little r, can be assumed parallel, giving the relation between their magnitudes as this, right? And let's understand that. So in the far field, this observation point here, this observation point goes to infinity, right? If it goes to infinity, then this observation point we can show is just going off to infinity, right? To infinity and beyond. And here we have this vector, which is supposed to also go from the source to the observation point, is also going off to infinity. All right. So the way we can approximate this vector R here, remember we need to find what capital R is. Capital R is equal to, we project this down to here, right? Now, this R is equal to this part of the little r. These are the same, right? So this part goes off to infinity. This part here goes off to infinity. If we consider from this dashed line onward, these two are the same length, right? So the only difference between big R and little r is this section here, which this section here, right? That section there is the only difference. So little r is longer than big R by this amount. So we can approximate big R as little r minus that amount. All right. So what is that amount? We have a triangle here, right? We have this angle here. We'll call that angle psi. Then this vector here. So we want the adjacent side now, right? The adjacent side is hypotenuse multiplied by cosine of psi. R times cosine psi. So we subtract that off from little r and we get big R. Now that's for phase variations. For amplitude variations, we don't need to be so precise. Why is that? Anybody have a feeling for that? Let's think about it. We're replacing R here, big R, with R minus R prime cosine psi. And the big R in the denominator for amplitude with just little r, which we know is approximate, right? Why does it matter more in the phase than it does in the amplitude? Yes.
The wavelength to meet the phase variation.
Very good. Yeah. So first off, beta is a very large number. So small changes in R, a small error in R, amplitudes to multiplies up to a large phase difference. And we're talking about interference here when we're talking about phase, right? So this small change in R, if we're not exactly precise, multiplied by a large number beta, can lead to a 180-degree phase difference, right? We can get destructive interference with that small amount of error, right? So we have to be precise with phase. Phase is very phase leads to constructed destructive interference, right? So you have to be very, very precise with it. And we're blowing up any changes in R with a large number beta. Now in amplitude, doesn't matter if you're, a kilometer or a kilometer plus 1 meter, the amplitude is going to be pretty well approximated, right? But a kilometer versus a kilometer plus 1 meter at 10 gigahertz, right? Could be a whole bunch of phase interference, could be a whole bunch of phase delay, and it could be destructive interference. Could lead to a very, very different result if you say 1,000 meters instead of 1,001 meters. All right. Okay, good. All right. So yeah, so let's plug in our approximations here now. It's called the parallel ray approximation or the far field approximation, where the observation point goes to infinity. Very common approach. And now we can go back to our magnetic vector potential spatial convolution integral here, and we can replace R with R minus R prime cosine psi, and the denominator replace with R, right? Okay, look what happens. So it seems like a trivial thing, but a lot of insight is going to happen. So e to the minus j beta R, remember R is unprimed observation. R prime is a source. It's a primed coordinate, right? And we're integrating over primed coordinates. So e to the minus j beta R over R can come out of the integral. And then we're left with e to the plus j beta R prime cosine psi. All right, so a lot of stuff has happened by that. First off, this part of the integral, let me see if I go into this in the next slide. Oh yeah, I do, good. Okay, so that's what happened, all right? All right, so let's understand the consequences. So A now is e to the minus j beta R, mu e to the minus j beta R over 4 pi R, integration over the source coordinates of j, e to the j beta R prime cosine psi ds prime, all right? We call that integral n, this integral, all right? Your book uses that, and a lot of your homework and stuff is going to involve the n integral. There's an L integral as well for the magnetic version, all right? For F. So N and L. When you solve scattering problems or you solve radiation due to current densities or aperture fields, then you will just it will reduce to calculating N and L, all right? Which is an integration. All right, so let's investigate further. We have A equal to mu e to the minus j beta R over 4 pi R. Then we have the integration of j e to the plus j beta R prime cosine psi. What is going on here with this? If we look in the far field, our spatial convolution is transformed into a Fourier transform, and we'll understand that. R dependence has been factored out. This R here, the observation variable R, is R, theta, and phi, right, of the unprimed. So we've explicitly separated the R dependence, the radial dependence, from the theta and phi dependence. Where's theta and phi in here, right? Well, okay, so R prime cosine psi, we can write as, let's say, R prime cosine of psi, and we'll see this later, can be the same as sine theta cosine phi x prime plus sine theta sine phi y prime if the source density exists in the xy plane. All right? You can say this is u x prime plus v y prime. All right? So now, look here. This here contains only theta and phi dependence, right? Which means the observation theta and phi, there's no R here. So this part of it does not change with distance, right? And remember what we said before, when we're in the far field, well, I think we even have that slide in this deck here, right? We said when we're in the far field, the pattern doesn't change anymore, right? The angular distribution, theta and phi dependence. At any given point, at any angle in the far field, the field is still decaying with R, it's still changing phase, but its angular distribution throughout space, the pattern, the radiation pattern does not change with distance. In the near field, it does, it's still developing, right? When you get to the far field, which is what we just saw in the mathematics, the pattern does not change. So look here. Here. still the absolute amplitude and phase is changing at a given R because of this coefficient. But that's just a complex number when you pick an R. The pattern is this theta phi dependence. That does not change your distance in the far field, right? All right, good. Furthermore, this is a Fourier transform because let me write it out like this. So we have the integration of J x prime y prime if it's in the x. So it doesn't have to be in the xy plane, but let's say the case that it is, e to the j beta x prime u plus y prime v dx prime dy prime, right? This is a 2D Fourier transform. It takes you from x prime y prime space, which is space, to uv space, which is angular space. U is theta phi dependent, right? So think about a Fourier transform in time. You go from a temporal signal, variation with respect to t, you do a Fourier transform, now you're in the spectral domain as a function of omega, right? This U is a spatial spectrum. We looked at that before when we talked about Fourier transforms, right? When we did the stationary phase and all of that. So this is a two-dimensional Fourier transform. Let's say this is only dependent on x then, right? So now we have j of x prime e to the j beta x prime u, and we integrate x prime out. So we end up with a function of u at the end. The spectrum, spatial spectrum, not temporal spectrum like you're used to in linear system theory, but spatial spectrum, all right? Spatial frequencies, different sinusoids with different periods spatially with respect to x, beta x, cosine beta x, right? Cosine 2 beta x, 3 beta x, different spatial variations of cosine, spatial periods that I can add together with different amplitudes to synthesize any periodic function I want. Doesn't have to be periodic though, right? If we're in a Fourier transform, it doesn't have to be periodic. All right, good. So we'll look at this more later. The far electric and magnetic fields can be represented, or okay, so once you have the A, right? You calculate N, you get A. Then multiply by mu e to the minus j over 4 pi r. Then you use all of this, right? So E far field is this, and H far field is that. We throw out the real or the radial components. E theta then, we have, okay, so E far field is this, but in terms of its components, ER is 0. E theta can be found like this, L of phi plus eta times N of theta, and E of phi can be found like this, right? These two are nothing but this expression, right? But in component form. And then you can find H in a similar way. So everything boils down to calculating N and L. And most of the times, you won't have electric and magnetic current at the same time. So you only calculate either L or N. Very nice. Okay, so we want to find the far fields in terms of their spherical coordinate components, right? Here we have the current density. So here's the N integral, right? The integration of J into e to the minus j beta r prime cosine psi ds prime. But the current density is in rectangular coordinates, right? At this point. So we want to transform into, if we're given a current density in terms of rectangular components, we want to transform it into spherical components. Because this integral, the way it's written right now, N, in terms of x hat, y hat, and z hat, what do we get over here for N? Because of the equality, what kind of components do we get over here? If you have an integration of a vector, what do? Right? I'm integrating x hat, y hat, z hat, these three components. How do I calculate that? What do you think? Very good. You distribute the integral, right? And because these unit vectors are not a function of x prime, y prime, or z prime, because they're rectangular unit vectors, they don't vary with position, then they're not a function of the integration variables. You can factor them out, right? Either way, they're not functions of the prime coordinates anyhow, right? But anyway, you would distribute that integral, right? So that means you're going to end up with rectangular components for N on the left. So now we want to calculate this N theta and L phi, right? Before, all we said was if you had L theta and L phi, then you would calculate. If you had L theta and L phi, and N theta and N phi, you can calculate E theta and E phi, right? But how do we get these N and L integrals in terms of spherical components? So that's what this slide is. So, okay, we use the transformation matrix. We go from, we represent X hat up here in terms of the spherical unit vectors. So X hat, if I have an X hat here, so I'm the Z axis, I have an X hat unit vector that way, right? I can represent that X hat unit vector in terms of R hat, theta hat, and phi hat using this matrix, right? So X hat is sine theta cosine phi R plus cosine theta cosine phi theta minus sine phi phi hat. And Y hat is sine theta sine phi R hat plus cosine theta sine phi theta hat plus cosine phi phi hat, right? Okay, so now we can say, we know what X hat, Y hat, and Z hat are in terms of these three spherical unit vectors weighted by these transformation matrix components. We can write the N integral as N of theta now. The theta component is the X component of current, Jx, cosine theta cosine phi, plus Jy cosine theta sine phi, minus Jz sine of theta. These are the integrals that you're going to calculate. And then there's N phi and L phi. So if you're given a current, this is the general case, right? You might just have some current in the XY plane that's only directed in the X direction. We'll do some examples. That means you would only have Jx, right? Because directed in the X direction. Jy is 0, Jz is 0, and all the M's are 0. So you'd have N theta or N phi, and you'd have N theta, but it only have these first leading terms, yeah? So it's the general cases here, but most times you won't. We'll do some examples. Here's an example. So I programmed these animations, hopefully they work. So consider, so this is the easiest case, right? It's a uniform aperture. So this might be a window in your house and you have the sun coming through. So it's not as nice of an example as sunlight's unpolarized and you don't know really okay, so you have a flashlight, right? With a polarizer on front of it. And then you just have some rectangular aperture and a big screen. And you kind of get a nice uniform field in the aperture. All right, so consider an aperture of an electric field all oscillating in unison. So here we have the script E, X, Y, Z, and T. Each of these vectors are oscillating in unison. They represent the electric aperture field. And that aperture field, each of these vectors are multiplied. Oh, so each of these vectors, E of X, Y, and Z, this is a complex E now with the standard font. Each of these vectors have the same length in the same direction. So the phase is the same. The complex vector has the same phase and same magnitude, each of these. When I add or multiply e to the j omega t to each of these, then they all oscillate like that, right? They oscillate in phase. All right, so the electric field vector at each point oscillates as the real part of this complex vector field, e to the j omega t. We know that, right? And all vectors are in phase. Hence, we may factor out the time dependence like we do for time harmonics anyhow, and obtain a uniform electric aperture field like that, right? So that's the whole idea. All right. What if there was a phase difference between, we'll do that case, I think, next. All right, so how can we represent this aperture field? E aperture is equal to Y hat. It's directed in the Y direction, right? This gray is a PEC screen, and then there's a hole in it, right? Y hat E naught. Okay, so it's constant. This vector field here is constant, right? And there's no phase difference between any of these vectors. They're all in the Y direction. They all have the same length, E naught. H aperture is minus X hat E naught over eta, right? And E aperture elsewhere. Okay, so this is outside of the aperture. Note, these fields have been simplified in order to reduce the complexity of the problem and hence may not adhere to the correct boundary conditions. Obviously, they're not, right? Who understood or who saw that? If this was PEC, what should we expect? What's wrong with this picture if this is perfect electric conducting, this gray ring? Very good. This tangential component has to be 0 at the wall, right? So these have to get weaker and weaker. They have to be 0 here. So this would be a sinusoid really, right? Or have 0 amplitude here. If I represented the amplitude of these vectors, they would be 0 here, then they would get bigger, 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 and then they would go back down to 0. when they got to that end. Okay, good. So what's the problem? We want to find the far radiated fields when this aperture A is 3 lambda and B is 2 lambda and plot the radiation pattern. All right, so let's do it. So as we will see next lecture, we can utilize equivalence principle to write equivalent currents representing the aperture field. We'll do that next lecture. But here we're going to just state that the current density can be found using this approach. J is equal to N crossed with H. All right, that is a boundary condition, right? But we'll have to formalize it more formally next lecture. Okay, so that's the normal to the aperture is Z, right? So we're assuming this is kind of the aperture where the current is, this gray square. Z is the normal. And we know what H is minus X hat E naught over eta. So we get minus Y hat E naught over eta. And M, we have an M as well, which is negative N cross E. So this is based on the Server's equivalence theorem that we'll learn next lecture. Negative N cross E, which is negative Z cross Y E naught, which is X hat Y or X hat E naught, right? All right, good. So we can calculate N theta first. And theta, we have the general formula for it, but we know we only have a Y component of electric current. So this X component goes away, the Z component goes away. We only end up with the Y component of current. Now we just have to solve this integral, right? What is R prime cosine psi? All right. R prime cosine psi is equal to R prime dot R hat, right? Because R hat is a unit vector, so it has unit magnitude. And if we calculate what this dot product is, magnitude of A, magnitude of B times cosine the angle between them. And that's exactly what this is. All right, good. So R prime cosine psi is R prime dot R hat. R prime, for the case of current density being in the XY plane, is X prime plus Y hat Y prime, right? Dotted with R hat, we know what the R hat unit vector is in terms of rectangular components, sine theta cosine phi X. This you'll never forget. Oh, are we missing some kind of parentheses? We are. This you'll, R hat in terms of rectangular variables, you're going to memorize this eventually because you're going to use it a bunch. X hat sine theta cosine phi, Y hat sine theta sine phi plus Z hat cosine theta. Okay, if you do that dot product, you get this. This is exactly what I showed you on the last slide. X prime U plus Y prime V, right? Good. So see, this is not a function of R because we're talking about R hat. R hat, the unit vector, is a function of theta and phi only. It doesn't have R because it's a unit vector. All right, good. So let's plug that back in here. N of theta, the integration over the X prime Y prime, JY cosine theta sine phi, e to the J beta, X prime sine theta cosine phi, Y prime sine theta sine phi, right? So you can do this numerically on MATLAB fast by just calling FFT. It's a Fourier transform, right? If you have sampled versions of JY. But anyway, we can calculate analytically. Minus E naught over eta is the current JY. It comes out of the integral. This is over prime coordinates. Theta and phi are not prime coordinates. They're observation coordinates. They're unprimed. They come out of the integral. And we just have to integrate E to the J beta X prime and so forth, right? Well, if you integrate this exponential, you get 1 over this multiplied by this again, right? The integral of an exponential. Integrate E to the JX, or say E to the J alpha X. Maybe that's a better way to. So the integration of E to the J alpha X dx is equal to 1 over alpha E to the alpha X, right? Because, or J alpha, sorry. If you differentiate that, then what happens? We differentiate this, we get J alpha coming in front, that cancels out, we get back to our integration, right? Antiderivative. All right, so, but what is this? This is a sinc function, right? That you can represent as a sinc function like this. So if you break, so this integration you can break into, what you can do is write this exponential as E to the J beta X prime sine theta cosine phi multiplied by E to the J beta Y prime sine theta sine phi, right? You can split it like that, and then you have two integrals like this that you do one at a time. And this you can write as sine of X over X. And, oh, why is it both sine X? Okay, one of these is Y, right? This is a Y, this is a Y. All right, so we know what the Fourier transform of a rectangle function is. It's a sinc function. We expect that. This is a uniform aperture, right? The current density is uniform. It doesn't vary with x prime or y prime. So we're taking the Fourier transform of a rectangle function. We know from linear system theory that that should give us a sinc function, and it did, right? Sinc in two directions, sinc in x and sinc in y. Now the x here is beta a over 2 sine theta cosine phi. And the y is beta b over 2 sine theta sine phi. All right, that's an easy integral to do, right? So let's see what it looks like. We can do, okay, so we can also do n phi, l theta, and l phi. Similarly, we get these results, and then we can construct the far fields using these formulas that we had before, l theta and n phi, and so forth, right? So we calculate all of these. Now we have e theta and e phi. We can plot it. So you guys will be making these plots in your homeworks, but these sometimes take some, you got to do one and then you understand how to do it. But these polar plots are kind of hard to do. Anyway, so what are we looking at here? Phi, right? Around the azimuth. Theta is represented as a, so this is like a polar plot, right? Let's see if this is the same kind of polar plot. No, this one's different, okay? So here we have azimuth going around, and we have theta going as the radius of a circle, right? So at different radii, this is theta equal to 0 at the center of this xy plane. Forget about the height off of it, all right? For now, we have at the origin of this coordinates, we have theta equal to 0, and it keeps changing theta until you get to this edge here, where theta is equal to 180 degrees. Theta is equal to pi. And then phi, you go around an azimuth. So do you understand? Let me draw something. So here, look, you have phi goes around, right? Theta goes this way. So theta equal to 0 is here. And theta equal to pi is here. And that's the same for all these radial directions, right? Theta is equal to 0 here and pi here, 0 here and pi here. But these are all different theta, different phi's, right? So now I just, on that grid, I plot the height as the pattern, e theta and e phi, because e theta and e phi are a function of theta and phi. So at each theta and phi in this grid, I can pick this point. It's some theta, depending on how far in radius I am, and some phi, depending on how far I am from the reference, which is, should be along the, in the xz plane, phi equal to 0 here. That theta and phi, I then calculate what e theta and e phi is, and I do the square root of magnitude of, or absolute value of e theta squared plus absolute value of e phi squared. And then I plot that value above this plane, and I get this witch hat looking thing. All right? All right, good. So what do we notice about this? Well, we have two side lobes along the E plane, in the YZ plane, where phi is equal to 90 degrees, right? We have two side lobes. And in the XZ plane, we have, it's hard to see, but there are, I think, 3 side lobes there. We have more side lobes, more lobes in the H plane, phi is equal to 0, than we do in the E plane. And that's because the aperture is rectangular. So it's wider in one dimension than it is in the other dimension. If you have a wider Fourier transform, right? This is a Fourier transform, yeah? So what do we know about Fourier transforms? If I have a wide rectangle function in space, what will the spectrum look like? Let's talk about time first, because that's something you've already studied. So if I have a rectangle function that's wide in time, what do I expect the spectrum to be? Wide or narrow? Narrow, right? It's an inverse. If I have a very narrow function in time, what do I expect the spectrum to be? Very wide. If I have a delta function in time, then what is the spectrum? Infinite. It's super wide, right? It's all frequencies to make a delta function. So there's an inverse relationship there. So if I have a rectangle aperture, the wider part of the aperture has a narrower beam width and more side lobes. Then the narrower part of the aperture gives me a radiation pattern that has a wider beam width and less side lobes. So the more you can remember your Fourier transform theory, the more you'll intuitively understand these radiation patterns. Okay, any questions on that? All right, let's do oblique case. All right, so here, what are we looking at? Consider a rectangular PEC plate. So before we had an aperture. So there was a PEC ring or a gray ring around our aperture field. But here we have a plate now. So there's a square PEC plate. All right. Excuse me. So consider a rectangular PEC plate of dimension A by B being illuminated by a parallel polarized uniform plane wave traveling in the YZ plane at an angle theta I with respect to the Z axis. Sounds like a homework problem, right? So you have, here's the X, Y, here's the plate, here's X, here's Y, here's Z, right? We have a plane wave coming in the YZ plane. So it's traveling in the YZ plane and it's parallel polarized. What is that? What does that mean? What is the plane of incidence in this case? How do we find the plane of incidence? You guys remember? Okay. You need two vectors to span a plane. The span of a plane takes two independent vectors, linearly independent, right? Okay, if you have two linearly independent vectors, you can describe any other vector in that space or in that plane as a function of these two, a linear combination of these two linearly independent vectors. So two vectors can describe a whole plane, right? The plane of incidence is the plane defined by the two vectors. One is the normal to the surface. The other is the incident K vector, right? So what is the normal to the surface? Z. What is the incident K vector? This vector here. So those two vectors are in the YZ plane, right? So the plane of incidence is the YZ plane. All right, if the plane of incidence is the YZ plane, then what is this polarization, TE or TM? Remember, TE or TM defines, it's with respect to the plane of incidence. So this electric field here, is it TE or TM? TE or TM? What is it? It is not TE, right? This, okay, so it might be hard to see it. This electric field is in the YZ plane, yeah? It's in the plane of incidence. They call it parallel polarization, means it's parallel to the plane of incidence, but this electric field is in the plane of incidence, is in the plane spanned by the incident K vector and the normal, the YZ plane. So it's not transverse to that plane. It's actually TM, right? The magnetic field is orthogonal to the plane of incidence or transverse to it. So TM, this is TM, transverse magnetic or parallel polarized. All right, good. So it's incidence in angle theta I here. Okay, so what's going to happen here? All right, so here's the Y direction, right? Here's the Y direction. Here's the X direction. Now, because this K vector is incident obliquely, then it's going to induce a phase delay because what is the X component of this K vector? The X component of this K vector is K naught, so Kx is equal to K naught times, in general, let's erase that so I can write it over here. Okay, in general, Kx, K naught sine theta cosine phi, right? But we know this plane of incidence has phi equal to 90, yeah? Well, yeah, phi equal to 90. So cosine of phi, wait a minute, Kx, oh yeah, sorry. So yeah, there's no Kx, right? Because X is this way, I thought X was that way. Kx is equal to 0, which we expect, right? Because this K vector has no X component. This is really Ky, right? Because this is the Y direction. So Kx equal to 0 because phi is equal to 90. Now Ky is equal to K naught sine theta sine phi. And phi equal to 90, or yeah, phi equal to 90 means that we get K naught sine of theta. So what does that mean? That means there is a K, there's a tangential K in the aperture, right? Ky means that K varies over the aperture. Now, if if theta was 90, means normally incident, then this would be 0, 2, right? There'd be no tangential K. That means you get the uniform aperture in the previous example because there's no tangential K. What is K? That's a wave number, right? Radians per meter. That means that there is a functional dependence. So this is a constant number, right? Because theta is fixed, some theta incident. This Ky means that there's this many radians per meter of phase delay, sinusoidal phase delay, right? So as I go 1 meter across the aperture, I get Ky amount of radians delayed, which means there's a phase delay in the y direction. Yeah? So here I'm plotting x as horizontal, y is vertical, but over here it's kind of rotated. Y is this way, x is that way. So if there is a phase delay in the y direction, look what happens in here. The electric field vector, so when we freeze time here, or we look at time harmonics, there is a phase distribution between, a phase delay, a phase relationship, phase delay between the vectors in the y direction because of this tangential K, right? So here, at phi equal to 0, or x equal to 0, y equal to 0, we have some vector, yeah? Now, in the y direction, we have these vectors have some phase delay between them. What does phase delay mean? These vectors have some cycle, right? They start off 0, they grow like this, then they go back to 0, then they grow in the opposite direction. So the phase delay between these is represented by a different length of vector, yeah? And if you turn time on, if you multiply all these by e to the j omega t, then you get this looking thing, which looks like they're traveling, yeah? Or the current is. All right, good. Okay, fine. So now the vectors representing the induced surface current density vector field are oscillating out of phase. Think of the wave in a baseball stadium. Although each person only oscillates up and down in their seat and does not change position, the wave appears to move around the stadium. So look at these vectors. Concentrate on this vector in this black circle here. This vector is not moving. It's oscillating harmonically, e to the j omega t, right? At a single frequency. It just oscillates. If it didn't even know anything about the other vectors, it would just oscillate up and down, right? Each of the vectors also oscillate up and down, but they start out of phase. They start out with these initial phases, and then they oscillate. So these phase delays depend on the incident K vector, of course. Now, what does it look like? It looks like the wave is moving, just like in a baseball stadium, but none of these vectors are really moving, right? They're just oscillating in place, but it looks like a wave traveling, right? All right. Because all vectors have harmonic time dependence, we may again factor out the time dependence and obtain a current density with a phase offset between vectors in the y direction. All right, good. Any questions? So the obliquely incident plane wave can be written in the following way. We know it's in the YZ plane, so it has a Y and a Z component, Y hat and Z hat, and its incidence in angle theta I. So you can decompose that parallel polarized or TM polarized incident electric field into these two components. And then the K vector, you can also do the same thing, right? We did that in lecture 4. All right, and then we have H incident similarly. Because the plane wave, we can find H incident using the right-hand rule and divide by eta. The induced current density is found from the boundary condition on perfect electric conductor. We know that, what is the boundary condition on PEC? You guys remember? Very good. Tangential E is 0. And in terms of the magnetic field, the discontinuity in the magnetic field is equal to the surface current, right? Surface current density. So J is equal to N cross H total, evaluated at the plate is equal to 0, which is Z cross H incident plus H reflected. Why do I only have H incident and H reflected? Yeah. Very good. And what does that mean? Very, very good. So the field on the other side of the plate is 0. No transmitted electric or magnetic field or electric field. So this is the total field here. H incident plus H reflected is equal to 0. We have Z cross H incident. We have parallel polarization. So we're going to use the reflection coefficient for parallel polarization to find what the reflected field is. in terms of the incident field. We are assured we put a minus sign there. Why is there a minus sign?
It's reflecting, right?
What?
It's reflecting, right?
Remember the difference between the reflection coefficient definition for electric fields, the ratio of E reflected to E incident, and the ratio of H reflected to H incident. Do you remember? Go back to lecture 5. There is a minus sign when we use reflection coefficient for magnetic fields. So gamma, let me write it down. Gamma parallel is equal to E parallel reflected divided by E parallel incident. But gamma parallel is also equal to minus H parallel reflected over H parallel incident. All right, why? Because of the convention we chose where the magnetic field in the assumed reflected. So whenever we defined or derived these reflection coefficients, we assumed the incident field had, so the incident field is going, this way. The K vector is the pencil, goes that way. The finger is the electric field. And the reflected field had the same direction of electric field, right? That was the convention we stuck with. But because the K vector switches direction for the reflected field, the magnetic field had to switch. So if my thumb is the magnetic field, then it has to be negative of itself when the field rotates, right? To keep the electric field the same. That's why the minus sign is there. Go back and look at lecture 5. All right, good. So, okay. So for PEC, one other thing is that we know that this reflection coefficient is -1 for PEC, right? Okay, so that gives you 2n cross HI, right? And this is called physical optics. We'll study that next lecture. That's equal to 0. So we can say, what is twice the magnetic field with n crossed? We get 2y hat H incident. We know what y hat H incident evaluated is equal to 0. So we put z equal to 0. We put z equal to 0 here. Z equal to 0 here gets rid of that. And then we end up with this, right? This is exactly what we plotted on the previous slide. Y hat, we got some constant field, but in the y direction, it changes. Remember, E can be thought of like a cosine plus J sine, right? So you can kind of think of exponentials as sinusoidal distribution with this kind of argument, right? So look, this is exactly what we plotted here. This is kind of a sine. So it starts out like that, goes to 0, goes here, goes to 0 again, and then it becomes maximum. If you plot it like this, right? So it's maximum here, 0 here, maximum here, but in the opposite direction, 0 here, and then maximum here in the opposite direction, right? All right, good. All right, so we calculate the n theta integral first. N theta is equal to, okay, so what do we have for our current? We only have a y component. So x goes to 0, z goes to 0. We end up with this y component only. We'll figure out what this argument is later. Oh, we'll figure it out now, actually. R prime cosine psi, R prime dot R hat. R prime here, we know that we're still in the xy plane. So we have source coordinates, the position vector, R prime is always in the xy plane because the current is always there, source. And R hat is the general form of R hat, which you'll remember, you'll use it repeatedly. Missing the parenthesis there, which is the same thing, x prime sine theta cosine phi plus y prime sine theta sine phi. So we calculate n theta. We have jy here. Here's the integration. This comes out of the integral, the cosine of theta and sine of phi because it's observation angles. And we're integrating over source coordinates. And here is our source coordinates now. Remember our j. Where's our j? Here. It has E naught over eta with a 2. So E naught over eta comes out. What happened to the 2? There should be a 2. Yeah, there should be a 2. Okay, and then we have to the minus j beta y prime sine theta incident. So here's that sine of theta incident, and it's on y prime. So now this exponential got a little more complicated, right? We had to combine it, the current one. This current gave an exponential that we had to combine with this one. We end up here. All right, but still it's a sinc function, right? You can do this. This is still an exponential integral. So we end up with this. Again, sine of x, this copy and paste errors. So, but now our x has this extra term in the y direction, our sinc function, right? So let's see what the consequences of that are. I guess the 2 is there now. All right. So now look what happened. Because of that sine of theta incident, our beam is no longer at theta equal to 0. It's no longer broadside to the plate. Because we came in at an angle, we induced that phase delay of current with the ky component tangential k to the surface. The current had a phase to it, and therefore we ended up with a beam which was scanned or reflected to an angle, right? Reflected to some angle not theta equal to 0. As a matter of fact, it's theta equal to 30 or so, right? So here's a cut. This is theta versus the amplitude at the scan plane, which is in the E plane, YZ. Remember, okay, so what is the E plane and H plane? I didn't explain that. E plane is the plane that has the electric field in it. And since we know that we were parallel polarized, and the plane of incidence was the YZ plane, the electric field's in the YZ plane, right? So we call the YZ plane the E plane. And obviously the magnetic field is the H plane, which is the plane containing the magnetic field, which is the orthogonal plane, XZ plane. Okay, so, and we have a certain number of side lobes in both directions. This kind of gives a 3D picture of the pattern. So the main beam is there, yeah? All right, so you come in obliquely, then you reflect in the specular direction kind of thing. You can think of it that way. PC is like a mirror, right? So if I come in obliquely on a mirror, then I expect my reflected beam to be having a peak, the reflected beam to have a peak in the specular direction, which means the Snell angle, right? Theta incident, theta reflected. Yeah? Okay. Good. I know the math shows that. All right, let's do one more. Far field and cylindrical coordinates now. So we have a PEC screen that's infinite. We have some kind of circular waveguide, which is bringing a aperture field into this circular aperture in the PEC plane. All right. Okay, so here's our n integral in general, right? And we have it in our rectangular coordinates we had before. Before we transformed it into spherical coordinates using the transformation matrix that took us to r hat, theta hat, phi hat from x hat, y hat, and z hat. But now we're going to use the cylindrical one. So instead of x hat, y hat, z hat being in terms of r, theta, and phi, it's going to be in terms of rho hat, phi hat, and z hat. Or no, I take that back, sorry. Before we transform the unit vectors, right? This is the key. Before we transform the unit vectors, x hat, y hat, and z hat into r hat, theta hat, and phi hat. And we ended up getting n theta, n phi, right? We're going to do the same thing. So we're going to keep that. But now we're going to transform the current. Jx, jy, and jz, we're going to transform into j, rho, phi, and jz. Yeah? Okay. So what does that? So this part stays the same. N of theta, we still have cosine theta, cosine phi from transforming x hat into theta hat. And cosine theta, sine phi from transforming y hat into theta hat. And sine of theta from transforming z hat into theta hat. Yeah? But now jx is equal to cosine phi j rho minus sine phi j phi. So we're going to transform the current as well, because it's most conveniently described in cylindrical coordinates with a cylindrical aperture. All right, we'll worry about r prime cosine phi or r prime cosine psi later. So n theta then, if you carry out this, what am I showing here now? Okay, so yeah, here, j rho cosine phi into cosine phi with cosine theta. So I distribute this, and then we have j phi into sine phi cosine phi. Okay, yeah, see? It's distributed everything to the next line. All right, now you'll notice this is super cool when you're doing a derivation and you end up with these things. Cosine phi prime plus sine phi prime, you get excited. And then this one too, sine phi cosine phi prime minus cosine phi sine phi prime. These are nothing but the cosine phi minus phi prime and sine of phi minus phi prime, right? So you can do some kind of trigonometric simplification there. All right, good. So that's that, yeah? So now there's our n theta integral. Okay, so now similarly, we can find n phi, L theta, and L phi in the similar way. So these are your formulas when you're solving problems in cylindrical apertures. So the phase function now, r prime cosine phi, we have r prime dot r hat. R prime we still write as x prime, y prime, and z prime. R hat we still write in the same way, x hat cosine theta sine phi, y hat sine theta sine phi, z hat cosine theta. Do the dot product, you get this, right? But now what you can do is you can take x prime and you transform it to cylindrical variables. X prime is rho prime cosine phi prime, y prime is rho prime sine phi prime, z prime is z prime, right? And if you do that, you plug r prime or rho prime cosine phi here and rho prime sine phi here, you can write this as rho prime sine theta cosine phi minus phi prime. All right, so it's a bunch of transformations, right? We're trying to get to cylindrical coordinates. And of course, ds, we know in rectangular is dx dy, but in cylindrical, we know it's rho d phi, right? Okay. So let's say we have a uniform aperture field here in cylindrical coordinates. So that means it's constant over the whole aperture and it's y directed only, but it's now a cylindrical aperture. We'll see that puts a signature on the far field, right? H is the same, and it's all for rho prime less than a. Following the equivalence principle again, we'll learn about the equivalence principle next lecture. The equivalent currents that lead to the appropriate radiated fields are M is 2n cross E, which is x hat 2 E naught, right? Because E aperture is y hat E naught. So N, which is Z crossed with Y, gives you X. And then we have 2 and E aperture, which is E naught. And 0 elsewhere. And there's no electric current in this aperture field. Okay. Since there's no electric current in the aperture, n theta equal to n phi equal to 0. That's one form of the equivalence principle. You'll see before we had an aperture field, but we had electric and magnetic currents in here that was based on the electric aperture field and the magnetic aperture field, right? So this time you should have asked, why don't we have an electric aperture current, right? Equivalent electric current in the aperture. If we do have a magnetic field in the aperture, we should have JS, right? But this is one form of the equivalence principle where we fill the back medium with PEC and we short out this JS. And then we use image theory to double the magnetic current. So this extra 2 here compensates for this J equal to 0. We'll see that next lecture. All right. So now we have L theta we can calculate, and L phi, those are the only two we need to calculate. L theta is the formula that we have derived for cylindrical coordinates. And what do we have here? Let's see. So we have, well, we only have an mx, right? Okay. And x, we know we can write in terms of, let's go back here. Jx or mx is going to give us a rho and a phi, right? All right. So we'll get a rho and a phi. There will be no z. So this will be 2 E naught cosine theta cosine phi. And we integrate from 0 to a rho prime. That comes from here. And so remember we calculated this on the last slide, which is nothing but r prime cosine phi. And we're going to integrate this over phi first. And then we have rho integration, d rho prime. So remember we had rho prime, d phi prime. So, okay, let me write it. ds prime, rho prime, d phi prime, d rho prime. Those are all there, yeah? And we said that r prime cosine of psi was equal to rho prime sine of theta cosine of phi minus phi prime, right? Rho prime that and that, yeah? All right, good. So, and then everything else comes out here. 2 E naught cosine theta cosine phi. Okay. Good. Right. So this integral inside of here. So I don't expect you to know this, but I'm gonna tell you. This integration here is equal to a Bessel function. We expect Bessel functions to show up in this integration, right? We expect them to show up in this problem because we're integrating something in cylindrical coordinates. We have some uniform aperture field in cylindrical coordinates, and we expect that the Bessel function to show its face, yeah? So there it is. By this integral identity. I don't know who derived this, but a lot of times when I need to find where these come from, I go to a book called Gradzhin and Resnick, which is a Russian book. Some Russians filled a huge book full of integrals. So, okay, there's the integral identity. As a matter of fact, this is in the back of your book for the course. All right, so the first integration becomes this, or becomes J naught 2 pi, right? So then, okay, L theta becomes that. Now we're gonna do a substitution. T, so we say T is equal to this argument. Therefore, dt is beta sine theta d rho prime, right? Okay, so if T is equal to beta rho prime sine of theta, then dt is equal to d of beta rho prime sine of theta. Well, we know theta is the incident angle, yeah? So, and beta is constant. So beta comes out, sine of theta comes out, and we end up with d rho prime. The d is like a differential operator, right? You guys have seen that in calculus 1. Okay, good. So now we can transform this integral into t. So, okay, so this beta sine theta d rho prime is let's see, 4 pi e naught cosine theta cosine phi. All right, if we divide by beta sine squared of theta, then first off, let's take the d rho. Oh yeah. So d rho, okay, so yeah, we're not done with the substitution, right? D rho prime then is going to give you dt divided by beta sine of theta, right? Good, so we can replace this d rho prime with dt divided by beta sine of theta, and we multiply by t here, right? So if we multiply by t, then let's write it out. So the integration. So we're going to start here, and we're gonna use all of our substitutions. 0 to a, we have j naught, we have beta rho sine theta is t. Then we have rho prime. So from this expression, we can say rho prime is equal to t divided by beta sine of theta. Yeah. So let's replace this rho prime with t divided by beta sine of theta. Now we have d rho prime. We know d rho prime from here is dt divided by beta sine of theta. So that gives you this beta sine of theta squared out front. And we just end up with t j naught t dt. Okay. Now, but this a here we have to transform as well because we were integrating with respect to rho prime. So when rho prime is equal to a, which it was here, what happens to t? T is equal to beta rho prime sine theta. That should equal to beta a times sine of theta. Yeah. So then we have beta a sine theta up here. Okay. So this integral. So here, this is also in the back of your book. This integration of a Bessel function multiplied by its argument over dz from 0 to delta is equal to j1 delta over 0. Yeah. This is just an integral identity. Or that's also delta j1 of 0. Because 0 is, we plug in with 0 for z here, that part goes away. All right, so then we have j1 now. So this j0 became a j1. We have beta a sine theta. So we have kind of a sinc function, but it's a cylindrical sinc function. And it's called the Airy disk function. j1 beta a sine theta divided by beta a sine theta squared. This is called the Airy disk function. We'll see it on the next slide. And we have all these coefficients, all right? All right, there it is. This is the sorting hat for Harry Potter. So, okay, so here, so we have L of phi. Similarly, we can find L of phi. Then we get E theta, E5 from our formulas, yeah? We could plot it here. This is a sinc function in cylindrical coordinates. We had a uniform aperture. We expect there to be no variation in rho, right? So that's what we have. So it is a area disk function. One nice property of these is you can tell for the rectangular sinc function from a uniform aperture. The Fourier transform of that is a sinc function, and we know sinc functions have a particular side lobe roll off, right? So we know the first side lobe is minus 13.4 dB with respect to the peak. And you can always check a radiation pattern. If it has minus 13.4 dB and nice roll off, then you know the aperture field it came from is a rectangle, nice uniform aperture. In cylindrical coordinates, this area disk function from a uniform aperture gives you 17.6 dB down from the peak, I think. I think so, yeah. Well, here, yeah, 17 dB down from the peak, right? Okay, very cool. Let me see what else we have. Oh, that's it. That's good. So we're ahead a little, yeah? All right, so next lecture, we're going to get into theorems and principles, and then we're gonna get into the meat of the course in the last lecture, which is scattering. And we're gonna do a lot of mode matching. You're gonna use all of the stuff you've learned in this whole course in the last chapter that we're gonna study in this course, which is scattering, all right? Very good, okay, good, I'll let you guys go, unless you have questions. Okay, get to your homework. There's a new homework out. Don't wait on it, all right? All right, see you guys. And I'll also announce the project next week for your extra credit project. How's it going? Sure.
If this is TM, shouldn't this magnetic field and E field be switched? Because the E field should be in the plane of incidence, or should be in the plane of incidence, and the magnetic field should be perpendicular to it.
I think the drawing's bad, right?
I
The
think
E
so,
field is
yeah.
in the plane of
Yeah,
incidence.
because then here.
Y,
we
Z,
show-
right?
Yeah, and this is purely an X.
Yeah, so TM means the magnetic field is transverse to the plane of
To the plane
incidence
of
or orthogonal to the plane of incidence.
Right.
So it should be in the X direction, yeah.
Okay.
Yeah, the figure's kind of drawn poorly. Very good. So you wanted to meet, yeah? All right. Follow me if you want. Yes, come to my office. How's it going, Xiaofen? The result from
Yeah, simulation.
the symmetry's bad, right?
Yes,
I went back and looked at the mesh.
Yeah.
The mesh is kind of coarse for the problem, I'd say. I think
Yeah,
our MoMA method did a better job at it. But I'd expect it to be symmetric. It's
yeah.
funny how that left side still matches well, though. We should maybe calculate the MoMA method result all the way out
How
to.
you can just plot a whole, 0 to 360 degree to see.
In the MoMA method?
Yeah, in the simulation.
Yeah, in our result, right?
Yeah.
Yeah. Yeah.
Can we combine two of them and submit a little bit later because
Well, yeah, we might.
qualifying exam is still complete, so it will be better if we can submit after Thanksgiving also.
Let me think about it. I might have to add some to it. So maybe you guys can turn them both in later, but there will be two that you'll have to do. Okay. Yeah, I don't mind extending the deadline, but we have to keep up with the. So that, we could probably do that. Yeah. All right. Okay.
Thank you, sir.
All right. How about that derivation?
No, I just started and I see all the ratio. Remember, we have something cross with mag and dot product of these larger vectors. can be written as something first cross with quadratic and then cross product. Okay.
So.
Mulai.